In this video, we're going to look at questions 3 and 4 from the voltage divider circuits tutorial, which starts on page 59 of the course notes. And these questions in particular come from page 60 of the course notes. And that's the course notes for Analogue Electronics Learning Outcome 1. So in question 3, we're told with a negative temperature coefficient thermistor, or NTC thermistor, and it's being used in a voltage divider circuit. Now, it should be clear from the graph that an NTC thermistor is going to have decreasing resistance with increasing temperature. That's what the negative temperature coefficient part of its name means. So we're given a graph which shows what its resistance is at different temperatures, and we're asked to find the voltage that's going to appear across this thermistor at different temperatures. So we need to do two things in each part of the question. Read the resistance of our graph, so we'll do that shortly, and then use the answer we get for the resistance to do our calculation of output voltage from our voltage transducer arrangement in the circuit that we have here. So let's tackle part A first of all. So here we're told temperature is 80 degrees Celsius. Now, although we're given the answer in the question, we want to make sure we actually know how we're going to solve a problem like this, because when it comes to TMA, of course, we won't be given the answers. So temperature is 80 degrees Celsius. What we're going to do is we're going to go to our graph and measure up from 80 degrees Celsius. And then we're going to measure across to our vertical axis to read off what resistance is there. And that's how we use a graph like this to find the resistance from a temperature. Equally, if you've been told with a graph what temperature does a particular resistance occur at, I want to read off the graph looking from the vertical axis to our slope and then down to temperature. So we can indeed see there's 1 kilo ohm. So the resistance read from the graph is equal to 1 kilo ohm or 1000 ohms. So now we have that. We're asked then what voltage is going to be found across this thermistor. Well, we know in an arrangement like this, the bottom resistor, or resistor 2, its voltage, V2, can be found using this formula. This is given in the course notes. I'll give you a page reference for this just now. At page 47 of the course notes, we get this formula. And sometimes we refer to this as VO for V output. We're going to write it V2 because it's the voltage across the second resistor in our transducer arrangement. So V2 is equal to the resistance across that resistor divided by the sum of the two resistances multiplied by the supply voltage. So in this case, R2 is the value that we've just calculated in part A, which is 1000. Resistor 1 is also 1000, 1 kilo ohm, that's given in the question. That's the top resistor on the diagram. And of course, resistor 2 again, it's 1000 there. Multiplying by the supply voltage of 5 volts, we're going to have 1000 over 2000 times 5, which is the same as a half times 5. So putting all of this into our calculator, we get 2.5 volts is the answer for 3A. Let's now turn to part 3B. This time we're asked the same questions, which we expect a very similar method here. But what we're doing this time is we're finding out the resistance, the temperature is now at 20 degrees Celsius. And so the resistance this time, we'll go back to our graph, and we'll use a different colour to differentiate this. So this time we use blue. I should say, if you're doing a question, there's no need for you to use different colours. I'm just doing it to try and make my working a little bit clearer here. So we measure up from 20 degrees Celsius on the graph, and then we measure across to our vertical axis again. And our graph's been drawn in such a way that it takes us to exactly 1 square up from 3, and moving up the axis of 5 squares between 3 and 4, which means that each square represents 0.2. So, as we're probably expecting to see, this means that the resistance here is 3.2 kilo ohms, which is equal to 3,200 ohms. To perform the same calculation as the same formula we used in part A, V2 is equal to R2, terrible R2, I'll rewrite that. V2 is equal to R2 divided by R1 plus R2 times Vs is supply voltage. There we have 3,200 divided by 1,000 because the first resistor's value hasn't changed, it's a fixed standard resistor. But R2 we still know, and this is multiplied by 5. So maybe not as easy to do this calculation. It's not going to be something nice and neat for us, so we should probably use our calculators. And of course, we can take another step here and say this is 3,200 divided by 4,200 times 5. And the answer we get out here, well, certainly rounded to 1 decimal place, is 3.8 volts. And again, that corresponds with the answer that we're given in the course notes, which are usually right, but it's always good to check. So what we can see is as the voltage drops, the voltage across the transistor is going to increase. And if we had some particular target voltage in mind that was going to power another part of the circuit, we can have a certain set point temperature at which the voltage is going to be a certain size across the thermistor, and we can use this as part of a control circuit. Question 4 asks us a simple question, which is what would happen to the voltage across the thermistor in the circuit shown as a temperature increase. So we've seen the effect of a temperature decrease, and the temperature decrease showed us voltage increasing. Well, it's tempting to therefore assume that the voltage would decrease as the temperature increased, and that's exactly what does happen. We can see that already, because if we were instead starting at 20 and then going to 80, we can see we have a smaller voltage moving in that direction. But also, physically what's happening is as temperature is increasing, resistance is decreasing, and a smaller resistance over the thermistor, while the first resistor is fixed at 1,000 kilo ohms, means that there'll be a smaller share of the voltage supply over the thermistor. And so that's why as temperature increases, voltage across the thermistor decreases. And so that answers questions 3 and 4 from this particular tutorial. And this is potentially a sort of question that we could give you in a TMA.